In this video, we're going to look at how to solve a trig equation with non-standard period like this using a graphical approach rather than using substitution. So the way we're going to do this is we're going to go ahead and use the cosine inverse to find our first solution. So we're going to say the input becomes the output, so pi over 4x is equal to cosine inverse of a half. I happen to know that cosine inverse of a half, that's a special angle. So let's say the angle that has a cosine of a half is pi over 3. And now I can go ahead and multiply both sides by 4 over pi in order to come up with my solution here. First solution, I get x equals 4/3. And there we go. We got ourselves one solution to the equation. Now, normally we want more than one solution, and so that's what we're going to talk about here is how to find those more solutions. This time, we're going to use a graph. So let me get out a nice big graph line here. And this is just a cosine function, so I'm going to graph a cosine function. Looks something like that. And I don't know how many solutions we need. I'm going to imagine that maybe we want like 3 or 4. There's a cosine function. I want cosine to be a half, and so I'm going to get the solutions. Let's see here. So we got a solution here, and here, and here, and here, and here. All right. So now in order to make sense of this, we're going to need to think about, first off, where does this solution land? And then we're going to need to think about the shape of the graph here a bit. So where is this solution here? Well, it's our first solution, and this is our first solution, and so it kind of makes sense to think that this value right here is probably 4/3, right? It's the cosine of 4/3, or if we plug 4/3 into this function, we're going to get a half. But let's think about what this function really looks like here. Let's think about period, for example. So the period of this function is 2 pi over 4, or in other words, 2 pi times 4 over pi simplifies to 8. So the period of this cosine function is 8. So that's 8. This is another 8. In case if it's useful, half a period is 4, half a period is 4. It would be 12 there. All right, so now let's go. What we'll do is use symmetry to help us figure out where these additional solutions are. So we know that this distance here is 4/3. Well, that means by symmetry, right, because from here to here, this part of the graph behaves just like this part, but mirrored. And so if this distance is 4/3, then this distance is also 4/3, which means this solution right here is going to be 8 minus 4/3. Using the same symmetry, this distance here is 4/3, so this must be 8 plus 4/3. This one, again, using the same symmetries, this and this are also 4/3. 4/3, 4/3. And so this solution here is 16 minus 4/3. This solution here is 16 plus 4/3. And there we go. There are solutions 1, 2, 3, 4, 5. If I needed more solutions, I could just extend my graph out here and follow the same pattern. By the way, this would be 24/3 minus 4/3 would be 20/3. This would be 24/3 plus 4/3 is 28/3, so on and so forth. So you certainly could simplify these answers down a little bit, but this is really the idea of what we're doing here. All right, so there's one example. Let's look at one more here. Let's go ahead and solve this one. So if we again use sine, the inverse function here, sine inverse in this case, 0.7. Let's see, sine inverse of 0.7, pull out my calculator, we end up with, that's 0.7754, divide both sides by 3, and we get my first solution for x, which is 0.2585 roughly. Okay, so we're going to try to do the same approach here of using a graph to find more solutions. So this time we need a sine graph. So sine looks something like that. And then we need a second. I'm going to go ahead and draw a couple, and that is a really poorly drawn sine function. I apologize, but let's just work with it. We're wondering, when is sine equal to 0.7? So we're going to end up with solutions here and here, and here and here, and there would be more here and here. And this one here is our 0.2585. All right, so then we're looking for this one, and this one, and this one. So we need to figure out what symmetries we can use here, but we also need to be thinking about the period of this function. So let's take a look here. The period of this function is 2 pi over b, so 2 pi over 3. So the period, if my graph starts here, this is one full period here, this is 2 pi over 3. This would be half a period. Half of 2 pi over 3 is pi over 3. This would be another pi over 3 further, so this would be pi. This one would be 4 pi over 3. That's right, that's 2 pi over 3s. All right, so now let's look at our symmetries. So this distance here is 0.2585. And it looks like our symmetry says that this distance here would also be 0.2585. So this solution is going to be pi over 3, as you can see here, minus 0.2585. This solution here, you can see from the graph, is going to be 2 pi over 3 plus 0.2585. This one here is going to be pi minus 0.2585. We had another solution here. It would be 4 pi over 3 plus 0.2585. And there we go. There's solutions 1, 2, 3, 4, 5. We end up with 5 solutions here, and we could just keep on going if we extended our graph even further. Now this technique is a little harder to use with something like a tangent function because the graph is a little trickier, but let's see if we can do it anyway. So we could again use tangent inverse. Oops, ignore the the point there. So tangent inverse of -4 is, let's see, tangent inverse of -4 is negative 1.3258. And then to solve for x here, we would multiply both sides by 3, and we'd have x equals negative 3.9775 roughly. All right, so there's my first solution. Admittedly, it's negative, but that's okay. And now we're going to turn to a graph to try to find more solutions. Now again, this is a little trickier because the tangent has kind of a weird graph, right? The tangent comes up like this and then wiggles like that, and then it does it again like this, and over here it would do it again like, try to get this roughly even here like this. And now normally, remember the tangent graph has a period of pi, but in this case the period is going to be pi over 1/3, or in other words 3 pi. So instead of this being at pi, this is going to be at 3 pi. You could also think of it as a horizontal stretch by 3, of course. So let's see. So this would be negative 3 pi. This would be, staying put at 0. This is 3 pi. These asymptotes, which are normally at pi over 2, are now going to be at 3 pi over 2 and negative 3 pi over 2. Okay, so now let's see how we can use the graph here. So we're looking for a tangent value of -4. The solution that we came up with already is this one here at negative 0.39. Oops. Let's try that again. Negative 3.9775. Okay, so this distance here is negative 0.39775. Now, where would my other solutions be? Well, here's another one, right, where tangent is -4. And how's my symmetry work? Well, it looks like this distance here would be the same as this distance here, and so this solution would be 3 pi minus 3.9775, and we could continue the same thing for another, right? This could extend over. Our next x-intercept here would be at 6 pi. Our next solution for this equation would be here, and this would be my symmetry, and so this would be 6 pi minus 3.9775. So you can do this same technique with the tangent functions. It just tends to be a little trickier because the tangent graph is a little weirder. But in any of these cases, you can use the graph as a way to come up with the additional solutions by looking at the symmetries involved.